Okay, let's just dive right in. Imagine this for a second. What if our whole universe, everything we see, isn't just expanding outwards, but it's actually like inside something way, way bigger?
Right.
And maybe the Big Bang. Maybe it wasn't really the absolute beginning. What if it was more like a bounce?
A cosmic rebound, yeah. That's hitting the nail on the head for where we're going today.
So, welcome to the deep dive. We're tackling a really out there idea today. Black hole cosmology, sometimes called Schwarzschild cosmology. It's this hypothesis that says our observable universe. It's literally the inside of a black hole, which itself is sitting inside some huge parent universe we can't see.
It's a pretty wild concept. Definitely pushes the boundaries.
Absolutely. So our mission here is to unpack this. We'll look at the theory behind it, how it tries to solve some big physics puzzles, the Big Bang, singularity, maybe inflation.
Stuff like that.
Yeah, and the sort of surprising bits of evidence proponents point to. And, of course, the major problems it faces. We want to give you a shortcut to understanding this, well, fascinating, if pretty speculative, piece of cosmology.
And it's interesting, the idea of objects trapping light goes back way further than Einstein, actually.
Oh, yeah. Before general relativity.
Yeah, back in the late 1700s, you had John Michell, Pierre-Simon Laplace. They were thinking about dark stars.
Dark stars using Newtonian gravity.
Exactly, just basic Newtonian gravity. If something was dense enough, its escape velocity could be faster than light. Light wouldn't get out.
Huh. So the concept was there, just not the right physics yet.
Right. It kind of faded when light was understood more as a wave, but the core idea lingered. Then came Einstein in 1915.
General relativity, the game changer.
Totally. Gravity isn't a force pulling things, it's the shape of space-time itself. Mass and energy warp space-time and everything else, light included, just follows the curves.
That geometric view is everything for black holes, isn't it?
Absolutely crucial. And almost immediately, 1916, Carl Schwarzschild finds the first exact solution to Einstein's equations for just a simple, non-rotating spherical mass.
And that solution gave us the blueprint for a black hole. Two key things, right?
That's right. First, the infamous gravitational singularity right at the center, R0.
The point of infinite density, where space-time curvature goes off the charts and, well, our physics just breaks.
Yeah, exactly. Penrose and Hawking later showed these are pretty much unavoidable in classical GR. A big problem.
Okay, so that's one big issue GR gives us. What's the other feature from Schwarzschild?
The event horizon. The Schwarzschild radius, that's the boundary, the point of no return.
Not a physical barrier you'd bump into, but cross that line.
You can't get back out. It's a true one-way membrane. Escape is geometrically impossible.
And inside, things get really weird with space and time.
Oh, yeah. They essentially swap roles.
Yeah.
Moving forward in time inevitably means moving towards the center, towards the singularity. All paths lead inwards.
That specific property sounds absolutely key for this BHC idea. The inside has to move towards the center.
It's fundamental because that inward pull is sort of reinterpreted in BHC as the expansion of space within the black hole. It's a very different perspective.
Okay, so that weird internal geometry, how did that connect to our actual universe? There was some kind of coincidence.
Right. The cosmological coincidence. It's quite striking. First, you've got the Hubble radius,
Which is basically the size of our observable universe. The distance light could have traveled since the Big Bang, roughly.
Yep. Now, calculate the Schwarzschild radius, the size of the event horizon for a black hole, with the total estimated mass of our observable universe.
Yeah.
Everything. Matter, dark energy equivalent.
Okay.
And the number you get is incredibly close to the Hubble radius. Same order of magnitude.
Whoa. Hold on. Why? I mean, one number comes from how fast the universe is expanding, the other from how much mass you need to trap light. There's no obvious reason they should match up, is there?
There really isn't. And for many cosmologists, it's just a coincidence. Interesting, maybe, but doesn't mean anything fundamental. It's only true right now, anyway.
But not for everyone. Some people saw more there.
Exactly. People like Rajkumar Pathria, a physicist, and I.J. Good, a mathematician, back in 1972. They looked at that number and thought, maybe this isn't a coincidence at all.
So they made the leap.
They did. They proposed that maybe our observable universe is the interior of a giant black hole. And that cosmic horizon we see, the edge of observability, maybe that's the event horizon of the parent black hole.
Wow. Okay. That's a huge conceptual jump. So if we are inside a black hole, what does that do to the Big Bang singularity? Does it just move the problem inside?
Well, that's where the modern versions of BHC come in. They don't just use standard general relativity. They bring in something more complex.
Something beyond Einstein?
Yeah, usually something called Einstein-Cartan-Siama-Kibble theory, or ECSK.
ECSK. Okay,
Yeah.
what does that add?
It adds quantum mechanics, specifically the intrinsic spin of fundamental particles, like electrons and quarks, and it introduces a new property to spacetime geometry, torsion.
Torsion. So space-time doesn't just curve, it can twist. Like wringing out a towel.
Kind of, yeah. It's a twisting or shearing sourced by the spin density of matter. Now, normally, its effects are absolutely tiny, negligible.
But not always.
Not at incredibly high densities, like densities you'd only find deep inside a black hole or right at the very beginning of the universe. There, torsion becomes hugely important.
And what does it do at those densities?
It creates a repulsive force, a very powerful one. Basically, the spin of particles interacting with this space-time torsion pushes back against gravity.
So it opposes the collapse.
Exactly. When matter gets squeezed down to near singularity conditions, this torsion-induced repulsion kicks in and fights against gravity.
Preventing the singularity.
That's the idea. It halts the collapse before infinite density is reached.
And Nikitin Papasovsky, he's the main guy pushing this model now, right?
He's probably the most prominent proponent, yeah. In his models, this repulsive spin-spin interaction is precisely what stops the gravitational collapse. No singularity. Instead, you get a bounce.
A bounce. So that's the Big Bang. Not a beginning from nothing, but a rebound.
That's the proposal. Our universe didn't top out of a singularity. It emerged from the collapsed matter of a black hole in a pre-existing parent universe. It bounced back from a contracting phase into our current expanding phase. A big bounce.
Which suggests maybe the universe is cyclical, keeps happening.
It certainly opens that door.
Yeah.
An endless cycle of collapse, bounce, expansion.
Okay, so if it bounces, how does it connect? Is there like a tunnel?
Pretty much.
Yeah.
The bounce phase is thought to create an Einstein-Rosen bridge, which we usually call a wormhole.
A wormhole, linking the inside of the parent black hole to our new universe.
Exactly. From our side, the opening of this wormhole would act like a white hole.
A white hole, like the opposite of a black hole. Stuff only comes out.
Precisely. Matter and energy pour out, but nothing can go back in from our side. And critically, we're causally disconnected. We can't look out through the wormhole to see the parent universe.
Okay, that's a lot to take in. It sounds incredibly elegant, almost. Does this BHC model actually help with some of the big headaches in standard cosmology, like cosmic inflation?
It definitely offers an alternative narrative there. Standard cosmology needs inflation, this period of hyperfast expansion right at the beginning, to explain why the universe is so flat and uniform.
And that usually requires inventing a whole new hypothetical field, the inflatoned field.
Right, which we've never detected. Papasovsky argues BHC gives you something similar without needing a new field. The sheer violence of the bounce itself, combined with intense quantum particle creation caused by the extreme gravity and torsion, naturally generates a powerful repulsive force.
So the bounce itself drives a period of rapid expansion, mimicking inflation.
That's the claim. It could potentially explain the flatness and homogeneity without needing an ad hoc inflat.
Okay, what about the biggest puzzle? Dark energy. This mysterious force speeding up the universe's expansion now. Does BHC have a better explanation than just a cosmological constant?
It offers a few possibilities, yeah.
Yeah.
They're still speculative, mind you. One idea is maybe dark energy isn't a thing filling space, but some kind of boundary effect from the event horizon of our parent black hole bleeding through.
Yeah. Oh.
Or maybe torsion itself, this space-time twisting, has some residual effect on cosmic scales that mimics dark energy. Another, more recent idea involves something called cosmologically coupled black holes.
Black holes that grow with the universe.
Yeah, the idea is they gain mass as the universe expands, and their collective gravitational influence, their pressure, could be what we perceive as dark energy, is trying to ground it in known physics, or at least extensions like torsion, rather than just adding a constant.
Interesting. And what about the arrow of time? Why does time only move forward? Standard cosmology usually points to entropy, right? Things getting more disordered.
Right, the thermodynamic arrow of time. BHC offers a more fundamental geometric reason.
Which is?
It suggests our universe basically inherits its arrow of time from the parent black hole. The event horizon is intrinsically directional. You can only go in, not out. That fundamental past-future asymmetry gets imprinted on the new universe born inside.
So times error isn't just about probability and disorder. It's built into the geometry from the start.
That's the proposition. A fundamental causal structure inherited from the parent.
And quickly, does it touch on other issues, like why there's more matter than antimatter, or the information paradox?
Poplawski has argued that torsion might also play a role in creating the matter-antimatter asymmetry during the bounce. And the information paradox, the problem of what happens to information that falls into a black hole if singularities destroy it, well, BHC solves it by getting rid of the singularity.
Information just passes through the wormhole into the new universe.
Essentially, yeah. It's not destroyed, just transferred.
Okay, this idea of universes popping out of black holes, it really screams multiverse, doesn't it? Like Russian nesting dolls.
Absolutely. It naturally leads to this nested, potentially infinite fractal structure. Universes within black holes, within larger universes.
Which sounds a bit like Lee Smollen's idea of fecund universes or cosmological natural selection. Is that related?
It's definitely related in the sense that both use black holes as universe generators. Smollen's focus, though, starting back in '92, was more about why our universe's physical constants seem so fine-tuned for life, or at least for complexity.
He applied evolution.
Sort of, yeah. Universes are born from black holes, their fundamental constants might mutate slightly in the process, and those universes whose constants make them really good at producing more black holes will have more offspring universes. Survival of the fittest, but for cosmologies.
So Smollen was about the why of constants. Poplawski is more about the how of the bounce mechanism.
That's a good way to put it. Smollen's is more evolutionary, Poplawski's more mechanistic. And Smollen actually made a prediction you could test.
Oh, yeah. What was that?
He argued his model predicted an upper mass limit for neutron stars, somewhere around 2 solar masses. Because if they got heavier, they'd collapse into black holes too readily, maybe disrupting the evolutionary balance.
And how's that prediction holding up?
Well, we've now observed pulsars, which are neutron stars, clocking in at about 2.08 solar masses. So that puts some definite pressure on that specific prediction from Smollen.
Interesting. So BHC paints this picture of a Tegmark level 2 multiverse, these nested realities, but always disconnected, right? We can't see the parent.
Causal disconnection is key. We can't see out, they can't see in.
But could there be other universes born from other black holes in our same parent universe, like sibling universes?
Logically, yes. If the parent universe had lots of black holes, then each one could potentially birth a new universe. We'd have cosmic siblings out there, parallel to us, but inaccessible.
Could they interact? Or could we ever know they exist?
Highly speculative, of course. But Poplawski has thrown out ideas. Like, what if 2 of those parent black holes, each containing a universe, merged in the parent cosmos? Could that cause our universes to somehow merge or interact?
Ooh.
Or maybe even just their gravitational pull on each other in the parent universe could leave some faint, large-scale imprint on our cosmos. Maybe some of those weird anomalies in the cosmic microwave background.
Right, the CMB, the baby picture of the universe. That's always the first place to look for weirdness. What does BHC predict we might see there?
Well, the main prediction relates to rotation. If our parent black hole was spinning, and most astrophysical black holes probably are, then our universe might have inherited some overall angular momentum, a cosmic spin.
And how would that show up in the CMB?
As subtle large-scale patterns, alignments or asymmetries in the temperature fluctuations that shouldn't be there if the universe is perfectly isotropic, perfectly the same in all directions.
Haven't we seen hints of things like that? Stuff like the axis of evil?
We have. There are these intriguing, though statistically low significance findings. The axis of evil, which is a preferred alignment of the largest patterns. A difference in power between the 2 hemispheres of the sky. A strangely large cold spot.
Things that look odd. And BHC proponents point to these.
They do, suggesting it could be the signature of an inherited cosmic spin. But, and this is a big, but these anomalies are faint. They might just be statistical flukes in the data, or maybe errors in how we subtract foreground light from our galaxy.
So not a smoking gun.
Definitely not. We need much better data, like from the upcoming CMBS-4 experiment, to see if these things are real and truly cosmological.
Okay, what about looking at the structure of the universe on large scales? The cosmic web.
BHC could potentially predict some subtle geometric distortions there, too. Things that might affect how light from the CMB travels through that structure, known as the integrated Sachs-Wolf effect. But again, these are very hard measurements to make cleanly.
Now, this next one sounds potentially huge. A recent JWST study, James Webb Space Telescope, looked at the spin of really distant galaxies.
Ah, yes, the 2025 paper. That caused a stir.
What did they find?
They reported an asymmetry. Something like 2/3 of the distant galaxies they observed seemed to be spinning clockwise, and only 1/3 counterclockwise from our perspective.
Which is weird because standard cosmology would predict a 50-50 split, right? No preferred direction.
Exactly. So finding a preferred spin direction in the early universe, well, that could be a direct sign of an inherited cosmic angular momentum, just like BHC predicts if the parent black hole was spinning. Popyovsky himself pointed to this kind of observation as a key potential test.
Okay, but there's always a catch, isn't there?
There is a big one here. The researchers themselves were very careful to point out a potential major observational bias.
Uh-oh. What kind?
It has to do with how we're moving. Our solar system is moving through space, creating a Doppler shift. This could make galaxies spinning one way appear slightly brighter or easier to detect than galaxies spinning the other way, especially at those huge distances.
So it might just look like there's an asymmetry because of how we're observing them.
Precisely. It could be an artifact of our own motion and observational limits, not a real feature of the universe. We need way more data, larger samples, and careful checks for these biases before we can say anything conclusive about cosmic spin from galaxies.
Right. So intriguing, but needs much more work. Any other ways to test this? Gravitational waves, maybe?
Yeah, gravitational waves open up new possibilities. For instance, remember that idea of cosmologically coupled black holes growing with the universe?
Yeah, one of the dark energy alternatives.
Well, if that's true, it should affect the distribution of black hole masses we see emerging with LIGO, Virgo, K-Ogre. We can test that distribution against the predictions.
And what about primordial black holes? The tiny ones may be formed right after the Big Bang or Big Bounce.
Some BHC models do predict primordial black holes. Gravitational wave detectors can also search for lensing effects, signals being bent by massive objects, which could constrain how many of those primordial black holes might be out there.
Okay, so there are some potential observational avenues, even if they're tricky or ambiguous right now. But let's face the criticisms head on. What's the biggest roadblock for BHC?
I think the biggest one, fundamentally, is falsifiability, or the difficulty of it.
Because the parent universe is hidden.
Exactly. The core claim involves a region, the parent universe outside the event horizon, that is, by definition, causally disconnected from us. We can't observe it directly. So how do you scientifically test that claim?
You look for indirect effects, like the CMB anomalies or galaxy spins.
Right. But as we saw, those effects aren't unique to BHC. They have other possible explanations, often simpler ones within standard physics. Without a clear, unique prediction that only BHC can explain, critics argue it borders on being more metaphysics than testable science.
And the physics inside the model, the stuff that makes it work, that's also a problem, isn't it? Torsion.
That's the other huge hurdle. The sophisticated versions of BHC, the ones that actually avoid the singularity using that big bounce, they rely entirely on ECSK theory, and specifically on torsion.
This space-time twisting.
Yeah. And the problem is, there is currently zero direct experimental or observational evidence that torsion even exists. None.
So the mechanism that saves the theory from a singularity is based on physics we haven't actually seen.
Pretty much. And conveniently, its effects are only supposed to be significant in places we can't look deep inside black holes or way back at the universe's birth. That makes it really hard to verify independently. You have to take this new kind of gravity physics on faith to some extent.
Okay, and then you compare all this to the standard model, lambda CDM, which, despite its own weird bits like dark energy, actually works really well.
It works astonishingly well. That's the elephant in the room for any alternative theory. SCDM, the standard model, uses just 6 parameters to fit an enormous range of incredibly precise data. The CMB power spectrum, galaxy clustering, supernova distances, the abundance of light elements.
It's a massive scientific achievement.
It really is. BHC, by comparison, is, well, observationally kind of impoverished. It doesn't currently offer a better fit to all that existing data. So Occam's razor, the principle of preferring simpler explanations, tends to favor ACDM.
Even with its mysteries like dark energy and the need for an inflaton field.
Even then. Because Phantom CDM's mysteries are more like placeholders within a framework that's incredibly well tested, BHC asks us to accept a whole new, untested theory of gravity, ECSK with torsion, to solve those mysteries. It's a different kind of conceptual leap.
So just to summarize the comparison, origin, singularity in CCDM, big bounce in BHC, inflation, inflaton field versus bounce torsion effect, dark energy, cosmological constant versus boundary torsion CCBH effects, arrow of time, entropy versus inherited geometry, observational fit, excellent for 50DM, circumstantial at best for BHC.
That covers the key differences, yeah.
And we have to come back to that coincidence that kicked things off, the Hubble radius matching the Schwarzschild radius for the universe's mass.
Right. It seems so suggestive at first.
But it's
temporary. The Hubble radius grows as the universe expands and accelerates. The Schwarzschild radius, if the universe's mass is conserved, stays roughly constant. So the fact they match now is specific to our current cosmic era.
It wasn't true in the past, won't be true in the future.
Exactly. Which leads critics to say it's probably just a cosmic red herring, a fascinating numerical quirk of the present day, maybe, but not something to build a whole new cosmology on.
Okay, so let's try and pull this all together. Black hole cosmology, it offers this, really coherent, maybe even elegant story.
It does have a strong narrative appeal.
It tries to wrap up multiple big problems: singularity, inflation, time's arrow, maybe dark energy, maybe matter asymmetry into one package. Using this bounce mechanism driven by torsion, there's a theoretical neatness to it.
A parsimony, yeah. But, and it's a huge but, it's built on that foundation of ECSK theory and portion, which is empirically unverified. That's the weak link.
So for BHC to really get traction, to move from the fringe to the mainstream, what needs to happen?
Two big things. On a theory side, we need more rigorous modeling. Really precise predictions about, say, the spectrum of density fluctuations coming out of the bounce. And crucially, predictions for observable signatures that are unique to BHC, things that standard cosmology or other alternatives can't easily explain.
Behind that smoking gun.
Exactly. And then on the observational side, we just need better data. Future surveys like DSI, Euclid, the Vera Rubin Observatory's LSST, CMBS-4, they'll map the universe in unprecedented detail. Maybe they'll find those subtle distortions or anisotropies BHC predicts.
And keep watching galaxy spins with JWST. Keep listening for gravitational waves.
All of that. We need independent tests from multiple angles.
So wrapping up, where does BHC stand?
Look, it remains a fascinating, intellectually stimulating idea on the fringes of cosmology. It's not the standard model, not by a long shot. Its reliance on unobserved physics, the difficulty in testing its core claims, and the overwhelming success of SCDM in fitting current data mean the burden of proof is incredibly high.
And it hasn't met that burden yet.
Not yet. The circumstantial evidence is intriguing, but far from conclusive. But that doesn't mean it's worthless.
How so?
Theories like this are valuable because they push us to question our assumptions. They force us to think about what might lie beyond our current understanding, to explore the limits of known physics, and to ask really fundamental questions about reality. Even if BHC turns out to be wrong, the process of exploring it can lead to new insights.
It challenges the status quo, keeps things interesting.
Yeah, absolutely. It's a testament to our drive to understand not just our universe, but whether there might be something even grander out there.
So, a final thought to leave everyone with. Just if, this seemingly outlandish idea turned out to be right, if our universe is inside a black hole, does that change how you think about your place in it all? Knowing that every single black hole we observe out there in the cosmos could itself be a gateway, a potential budding universe, maybe even a child of our own universe, continuing this nested cycle potentially forever, makes you think, doesn't it?